You did?
It's really funny.
I'm going to have to call your mom and dad.
They're going to be like, she's really funny. It's okay.
I talked about how ionic compounds have to be solid. They're all solid at room temperature because of the arrangement and the attraction of the oppositely charged particles. That's not true for molecular compounds. Molecular compounds either stick to each other or don't based on how attracted molecules are to one another. We know that water is a polar molecule. The oxygen side, like over here where I'm pointing on this molecule, that's negatively charged because the oxygen is drawing the electrons away from the hydrogen. And down here where the hydrogens are, that's positively charged. They have a partial negative on one side, partial positive on the other. Well, the negative side of this molecule will be very attracted to the positive side of that molecule, so that draws water molecules together, and it causes the water to be a liquid. We don't have that separation of charges in oxygen or any diatomic because they share electrons so nicely. So there's no positive side or negative side. And so oxygen molecules don't really have anything that attracts them together. So they just float around free as gas particles. So with molecular compounds, the attraction for particles, which we call intermolecular attractions, that dictates the physical state of them. We'll have a lot of focus on this kind of thing. We have to talk about the shapes of molecules because this, well, and then the electronegativity and whether they're polar or not, there's all that plays into it. And the shape matters too. Like CO2, you've got polar bonds in CO2, but since it's a linear molecule, they cancel out. It's a nonpolar molecule overall. All right. Now, one other slide about metallic and ionic, just comparing and contrasting ionic compounds to metallic compounds. Because both ionic solids and metallic solids, they arrange themselves in crystals. It's a very orderly arrangement. A little bit more orderly in ionic. But ionic solids cannot deviate from their shape, or they're going to break. You're surprised, and that makes it even better.
Guys, you know the basketball team.
It's from this page that I have a link to this animation I want to show you.
We get to watch it.
We are going to watch it. It's not exciting. It's actually quite boring, and it goes just a little bit too long. So I do apologize for that in advance, but they've got this wonderful piano music that will soothe you. And all this angst that you have built up, it's going to be good.
You hear that, Pasta?
Yes.
You won't be awake at the end, at least, but you won't want to go and hurt yourself.
There you go. Were you behind me? I knew you were behind me.
I wanted to sleep so bad.
It was so uncomfortable, but I was so tired.
Me and my friend both fell asleep on each other.
I don't know how loud this is going to be when it starts.
I fell asleep like this. I literally just put my head on my shoe.
We have to take ours today.
What chapter?
Cold War. Oh, I legit, that's like
Meet Wallabout.
legit like, not that well about.
Map your walls.
Meet Wallabout DIY. This device shows you an exact image of what
Yay!
behind
Such an interesting texture.
That was the ad.
You can skip it.
Trying. All right, here it comes. Isn't that nice?
Metals are shiny, malleable, ductile, and good conductors of heat and electricity. The structure of metals and the nature of metallic bonds explains some of these typical features. Metals are made up of positive ions closely packed together in crystalline solids. The positive ions are surrounded by a mobile sea of electrons. These valence electrons are free to move away from their atoms of origin. When one electron flows away, another one moves in to take its place, due to the electrostatic attraction between the cations and the electrons. This is the nature of metallic bonding, what holds a metal together. Compare this image of a collection of cations surrounded by a mobile sea of electrons with ionic bonds, where oppositely charged ions are held together by electrostatic attraction, or covalent bonds, where two uncharged atoms share their valence electrons. Metallic bonds are much weaker than either ionic or covalent bonds. The highly mobile sea of electrons is responsible for the shininess of metals. Photons of light are more readily absorbed by free electrons, which can easily jump to a higher energy level. Then, when they fall back down a level, the energy is re-emitted as light. The color of the metal is determined by the wavelength of light which is re-emitted. Similarly, this free flow of electrons explains the ability of metals to conduct heat and electricity. When you heat up a metal, the free electrons quickly start vibrating. Increased kinetic energy
The whole
means
atom
increased
vibrates. So you got
temperature.
this one wrong.
When an electric current is applied to a metal, electrons enter from one side,
This part's
causing
good.
repulsion and generating movement within the sea of electrons.
Nice.
Satisfying.
And it electrons
I love that sign comfort.
as the metal. The mobile sea of electrons also explains the malleable nature of metals. If you strike an ionic crystal with a hammer, it shatters. This is because the applied force pushes like ions close together. They violently repel each other, breaking the crystal apart. In contrast, if you hit a metal with a hammer, it doesn't break, it just dents. Metals are able to deform in response to an applied force. The mobile sea of electrons shields the cations from each other, preventing violent repulsion and allowing the metal to change shape. The most malleable metal is gold. A similar property to the malleability of metals is their ability to be pulled into long, thin wires. We call this ductility. Ionic compounds are not ductile for the same reason they are not malleable in general. If an ionic compound is forced into a long cylinder, it breaks apart because of the repulsion of like ions. In contrast, a metal can be pulled into a long cylindrical shape because the cations can line up, shielded from each other as the fluid-like sea of electrons flows around them. The most ductile metal is platinum. Almost all metals are solid at room temperature, the cations forming a recognizable, tightly packed shape. Can you think of the exception? Mercury is the only metal that is liquid at room temperature. There are 4 other metals that melt very close to room temperature: francium, cesium, gallium, and rubidium.
Yeah, little owl.
Is that all the pieces?
That's it. You want more?
Owl.
It's like elevator. But I was expecting it to just.
What elevators do you
Oh.
Really? Don't you hear this in elevator?
No, I hear like they don't even play.
Wait,
They
yeah,
don't even play like that
You
type
gotta
of
get
music.
popcorn.
They play like pop songs and
Yeah.
like
You gotta
What's that?
get popcorn right. Is your plate? in the background.
Oh man, all the people that watch, somebody's gonna narc on here.
You're standing there.
Don't suggest anybody likes this one.
Right in the middle. It's really funny.
Unless somebody's recording video.
I would like to thank Socratica for the use of that, even though you didn't give me
I
permission.
just don't want it. I'm not.
I love the lady.
I'm not bold like that though. Like some people have done some very odd stuff.
All right, I have one other thing about covalent solids, and that is something that it does show up quite a bit on AP exams. Maybe not every year, but frequently. They'll ask questions about network solids. Network solid, there's only a few network solids out there. The most well-known one is diamond. So look for silicon carbons and silicon compounds, and diamond. Diamond is a pure form of carbon, because carbon can make 4 different bonds. If a carbon is bonded to 4 other carbons, and each of those are bonded to 4 other carbons. Now you keep in mind these are not 90-degree angles really, they're tetrahedral in shape. That's why they can spread out more than that. That's a better description than this is. But and these ones close to each other are not actually touching, they're in a different region in space. But yeah, a diamond is one big molecule. It's all these carbons attached to other carbons, which are attached to other carbons, and it just perpetuates itself out. And a good diamond is one molecule. And that's what makes diamonds so hard. You can pound on a diamond all day long, and it's not going to break if it's a good diamond. Well, it would have one with imperfections in it, though. A good diamond is real expensive.
Well, aren't diamond prices all like, what do you call it? Monopoly?
I don't know
So
that
like
one.
I thought there's like one company owns like 90% of diamonds.
Oh, yeah?
Yeah, they make
Oh,
like
yeah,
fake
that's
scarcity. Yeah.
You should know this information.
I didn't know that. Yeah, they say graphite is a network solid too. It is a bit more complex because graphite really is not one big molecule. I guess you could make a case for it because there's the carbons in graphite are not. They don't have one single bond to 4 other carbons like they do in diamond. They usually are bonded to 3 other carbons, and then that 4th bond that they can make, they're making a bond, another carbon in a different layer. And there's pi bonding that is involved in graphite too. And that's why these layers kind of slip past one another. I think you can make a case either way that graphite is either a network solid or it's not a network solid based on its structure, but often it's in the conversation with network solids. Another very well-known network solid is SiO2.
That was sand is.
Yeah, sand primarily is silicon dioxide. Yeah.
Oh
It's gonna be in the video.
Matt Barker. Getting phone calls during class.
Yeah, make sure colleges don't see that.
Yeah, so do know this about network solids. They're the hardest of materials. Diamond, there's this hardness scale called the Mohs hardness scale. And diamond is number 10. You know that one from Science Olympiad, right? Yeah. Diamond is the top. What else is up there with diamond?
Corundum is 8. Okay, wait.
Yeah, so diamond's 10, and then the next one is corundum. Yep. Where's quartz at?
7.
Okay, so quartz is real hard too. And sand is really a type of quartz, silicon dioxide typically. The form of it is
like
quartz.
sand on the beach.
Yep. Yep.
Oh, it's white sand.
So know that these have, even though they're made up of all nonmetals, when you generally think of things that are covalently bonded, they normally don't have high melting points. Ionic is normally a higher melting point than covalently bonded things. But if it's a network solid, because it's one big molecule you're trying to melt down, that takes a real high amount